So we consider our Lagrangian, which is a function of q alpha dot, and t, and we want to make a new function. So we want a new function that will involve q alpha, p alpha, and t. And we will give that function the symbol h. And we're going to apply the Legendre transformation. And we'll simply state that h of q alpha, p alpha, and t will be our sum over all the coordinates of q alpha dot p alpha minus L of q alpha dot and t. So recall here that p alpha is our partial with respect to the partial of the Lagrangian with respect to the velocity. So this is a Legendre transformation, and we're introducing our function u that we used in the transformation is this p alpha. And if you recall, we had this u defined as df by dx. So our variable x that we used in the previous example is this q alpha dot. And that's the variable that we are eliminating with this Legendre transformation. So the only difference is that we've introduced overall a minus sign. So in order to proceed, I'm going to start looking at now the total differentials so that we can equate things on both sides. So let's look at a differential dh, and I'm just going to stick with this function. So it's my partial of this Hamiltonian with respect to q alpha dq alpha plus a partial with respect to p alpha dp alpha plus a partial with respect to time dt. So that's the total differential. Now I'm going to also use that on the right-hand side of this equation. In order to keep it clean, I'm going to drop this summation sign. So just think that it's there in all of these expressions, but otherwise it's going to get very messy because I should really have a summation sign here over alpha, a summation sign here over alpha. We're not going to lose anything by dropping it for now, and then we can reinsert it back when necessary. So the first thing I want to do is take a derivative with respect to q alpha dot, and what I end up with is p alpha dq alpha dot, and then minus dl by dq alpha dot dq alpha dot. So that's from these two terms. And then I will also have a term that's q alpha dot dp alpha. So that's taking a partial with respect to p alpha plus dl by dp alpha dp alpha. Oh, that should be a minus. di L by di P alpha dP alpha. So I've taken Q alpha dot, I've taken P alpha. I need to now also take a partial with respect to Q itself. So there's no contribution from here. So I have a minus di L by di Q alpha dQ alpha. And finally, the time, minus di L by di T dt. So these are all of my terms. So now we can look at the dependence on these two lines for specific quantities. So notice that there's only one on each side that involves the time. So instantly I can say that dH by dt is minus di L by di T. So that's a key equation. Now I look at terms that involve Q alpha dot. There is no dependence in this top line on Q alpha dot at all. That's by definition. The Hamiltonian is never written with a velocity dependence. And so that means that the terms with Q alpha dot have to vanish. But of course, P alpha is defined as di L by di Q alpha dot. So those conveniently cancel. Now I have a term that depends on dQ alpha. And so I can also write that di H by di Q alpha equals minus di L by di Q alpha. So the term we have remaining involves dP alpha, but notice there's this partial derivative with respect to the momentum in the Lagrangian. And of course that vanishes because the Lagrangian does not depend on the momentum. So that implies that these two terms have to be equivalent. And so we then write down that Q alpha dot is equal to di H by di P alpha. So we have these three equations for our system involving the time, involving derivatives with respect to Q alpha, and then a derivative with respect to P alpha. So notice how the velocity is defined. So the generalized velocity is the derivative of the Hamiltonian with respect to the momentum.